Okay, so welcome everyone. Today we'll talk about kind of the last variant of the Kalman filter, or which belongs to the family of the Kalman filter framework, which is the sparse extended information filter. So last week we actually discussed the extended information filter, which is one technique which basically does extended Kalman filtering, but not in moment form. That means using mean and covariance matrix, but which uses the information vector and the information matrix to do the filtering. And you can show that both filters have actually the same expressiveness. That means they estimate the same state, or can estimate the same distribution, the Gaussian distribution. Let's better put it that way. And so the errors that we do or approximation errors that we do in the EKF, we do them in exactly the same way also in the extended information filter. The difference between the extended information filter and the extended Kalman filter was that different steps have different computational costs. Inverting a matrix obviously is the same, but conditioning and marginalization are two things where one is easy in information form and the other one is easy in moment form. And depending on what we are doing, one operation can be more efficient than the other. But in the end, if we put everything together, it turns out that for the Kalman filter, the prediction step is computationally cheaper and the measurement step computationally more expensive. And for the extended information filter, it is the other way around. So the question is, what do I need to do, or is there any big gain from using the one or the other form? And it turns out that they are both kind of similar. There may be applications where the extended information filter is a little bit advantageous, and there are techniques where the extended Kalman filter may be advantageous, but there's no really clear winner. What we're going to do today is to discuss an extension of the extended information filter, which is the sparse extended information filter. So we're talking here about what happens if the matrices that are involved in the computations are sparse matrices. And this turns out to be highly advantageous if we operate in information form. And so we will discuss today and actually next week, because I didn't manage to squeeze everything within 90 minutes. I tried so, but then I kind of revoked that and split that up into two parts. So today we will discuss the prediction step and the update step of the sparse extended information filter, already tailored to SLAM to have, let's say, at least some more concrete examples. And then next week do sparsification and mean update steps, which are two additional steps which are needed. So today I would like to give you the insight, what makes the sparse extended information filter a good idea, and we will discuss the two main steps. It's involves a little bit more math today, so there are quite some derivations. I tried to not go over them very quickly, but to give you really an insight what happens here. And the math is, everything is on the slides, and I hope I present them in a way that you can actually understand every single operation that we do. And so if there is anything unclear, just interrupt me and say, hey, I don't understand this step from whatever line 18 to line 20, what's going on here, and I will try to explain that to you as good as I can. So the goal today is, even if you don't keep in mind all the individual steps that the sparse extended information filter does, which I think you won't, at least you should know what are the key steps toward the goal. And if I would need to do it myself, I would be able to do it, or to derive it myself. That's kind of my goal today. Of course, there are some tricks involved, and without someone telling you the trick, you won't be able to do that. But let's say, if given that you have a sheet of tricks or some rules that you will apply, you should be able to actually derive the steps yourself. So as a short reminder, what we had was, in the extended information filter, we used the canonical representation or the information form for doing all our operations. And what I'll try to do here on the blackboard is at least note down a few things that you probably need to keep in mind today, so that you have it always at hand. So the covariance matrix that we have, the inverse of the information matrix, and the mean can be computed by the inverse of the information matrix times the information vector. So that's the first part. How do the moments look like? And the same we can do the other way around. So we have the information matrix is obviously the inverse of the covariance matrix, and we have there the information vector is the inverse of the covariance matrix times the mean. And that was the inverse of the covariance matrix times the mean. These are just two things I noted down here, so whenever you forgot about it, you can actually look it up on the blackboard here. And we might need that during our operations. So we all know there are two ways to represent a Gaussian distribution. One is the standard form, moment form, and the other one is the information form or canonical representation, parameterization. And they are equivalent in the sense of what they can compute. They both represent a Gaussian distribution. Okay, now let's start with the sparse extended information filter. So, and to motivate the approach, why it makes sense to use a variant of the extended information filter, which is a sparse extended information filter, which is an approximation of the extended information filter. So it's not an exact operation. So the result we get will be worse than the extended information filter or the EKF. But, as we can show, it has some very nice properties from the computational point of view. Namely, it will turn out that we can do the involved operations here as constant time operations, which is something which is a dramatic increase in computational resources. Okay, if you look to a standard SLAM problem, so we have a map of landmarks and we have a robot moving around in the environment, as you can see it here on the left. So what you see here is the robot is sitting over there. You can see the trajectory that the robot took all through the place, and it observed landmarks. These are the landmarks shown here, and they're kind of these blackish, blurry areas that should kind of represent that this is a Gaussian distribution. So you have roughly spherical covariances for the individual landmarks, so you have a pretty good idea where they are located. And if you look into our covariance matrix, we actually get this dense covariance matrix. And it has this checkerboard pattern. That means all the x locations and all the y locations of the landmark are strongly correlated. But there's no or little correlation between x and y of the individual landmarks. So if we fix the x position of one landmark, we basically know the x position of all other landmarks quite accurately. That's what this pattern here reveals. The problem is if I have a matrix like this and I need to invert such a matrix, this is a quadratic number of elements, so this is a costly operation to do this inversion. If I, however, look to the information matrix, so this is a normalized information matrix, that looks not that dense. So this is kind of the inverse of this guy. This guy, however, is pretty dense, so these values which are here shown in white, they are not exactly zero. They're just small elements. It's also kind of densely filled. But at least if I visually look to that, I should see that there are elements which are much, much stronger than other elements. So if I can zoom in and see this pattern over here, I see, for example, elements like this, the post probe which sits over here, and there's some strong correlation with some element down here. Because of these, or there's a strong link between them. But the important thing is all other elements here are also non-zero, but they're very small. So they're close to zero, but they're non-zero. And now I can ask myself, if I have this matrix, let's say from, just to motivate the work, may I put everything which is smaller than epsilon to zero, and then I have a sparse matrix, and then I can do my operations more efficient. So the sparse extended information filter is somewhat more involved than this, just set everything to zero, which is really small. So it's not that easy. But it will allow us to build up an information matrix which is sparse and which will maintain sparse during all the computations. And this then is a great advantage for all the operations that I do. So the first thing I would like to do is kind of get a little bit more interpretation into this information matrix. So what does it mean in this information matrix? The nice thing is we can actually nicely visualize that if we say, okay, what we have in here, the first three coordinates, first three dimensions are the position, represent the position of the robot. And then the other elements are, let's say, represent the position of the landmarks. Yeah. So we have the robot over here, and we have these elements here should be landmarks. And there's something which is called an active landmark. These are kind of the black things here, and we have so-called passive landmarks. The active landmarks are typically those landmarks that the robot is either currently observing or where there's currently a link between the robot's pose and the landmark pose. And the thing is, it can actually interpret this matrix as a graph. So, and every element which is non-zero means that there's, okay, Let's start from the beginning. So they can be represented in the graph in the sense that we have nodes, and these nodes represent the random variables or the individual dimensions of my problem. So I have a node for every dimension I have in here, or I can actually group them, so I have a better interpretation of them, like the pose of the robot is one node, and every landmark can be seen as one node. And then whenever I look to this information matrix, I can see the information matrix as the matrix which tells me which nodes are connected with an edge. So if there is a non-zero element in this matrix, that means there's an edge connecting those two nodes, and this edge imposes a constraint or a link between them. So if the robot's pose is here, and it makes an observation, this kind of can see that there's a link which is created to the landmark it observed, and then there's a constraint which results from this observation. And kind of the darker the off-diagonal element in here is, the stronger the link, the more information sits in this link. The more I know. Yes, please.
But, you said that every element is non-zero.
Yes.
So there's always a very, very small link from every node to every other node?
Exactly. So you can see this as a fully connected graph.
Okay.
Well, but let's say the landmarks which are very, very far away, which haven't been seen at the same time, and where the robot took a long time to travel from A to B, they will have a very, very weak link. But that's absolutely right. If I take the exact information matrix and I would build up the graph like that, every node, or basically more or less every node, would be connected with every other node. So there would be no win in this sense. But what I want to talk here is about kind of how do I interpret this information matrix. But you're absolutely right in what you're saying. And you can actually show that what and the idea that we are trying to do is that we kind of say we only want to maintain this information matrix kind of in the correct way for a small number of features. For the ones I see right now where there's a strong link between the robot's pose and those features. And these will end up to be these active features. And then there are others which are further away, which I haven't seen for a while, whatever we say. The correlation between the current pose of the robot and those landmarks is rather small, and I'm going to ignore them. That's kind of the approximation that we are, or I could try to get rid of those edges. That's something we are trying to do later on. And then this gives us a sparse graph. But if I interpret it, if the matrix is fully populated with elements, although they are small, it will result in a fully connected graph. And for those of you who attended the AI course and may not know something about graphical models, you can actually show an equivalence between this information matrix and a Gaussian Markov random field. So I have every node, which represents here to whatever the landmark or the robot's pose, is a random variable, and you have those constraints between them, which correspond to the potentials you have in a Gaussian Markov or in a Markov random field in general, but here Gaussian Markov random field because we're living in a Gaussian world. I'm not going to elaborate that in much more detail, but for those of you who attended the AI course know something about Markov random fields, at least they can see a connection between them. And if I have two nodes which are not connected via an edge, so there's no edge between them in the graph, that means that they are conditionally independent of each other given all the other nodes. This is something you may know from different graphical models that you have seen, also Bayes networks. You have the directed links, but you can also model similar things with that. So whenever there's no edge between two nodes, it means they're conditionally independent given all the rest. So given I know all other nodes, these two are conditionally independent. If I don't know all the others, they are not independent of each other. It's just because if we draw a simple, very, very simple graphical model. So you have your nodes. Let's say it looks like this. So this is node 1, 2, and 3. So what this means is if you know the node number 2, 1 and 3 are conditionally independent of each other. But if you don't have any knowledge about 2, then the knowledge about 1 will also tell you something about 3. But given you know 2, they are independent of each other. This is the conditional independence, and this is exactly what how we can interpret two nodes which have 0 elements in the ith j's row column. So if you have node I and node j, and the element ij is 0, that means they're conditionally independent of each other given we know all the rest. It's kind of the direct interpretation of that. And the individual element, so how large this value is in the information matrix, tells me how much information do I have, how much do I know about this constraint. So you can see that the larger the value is, the stronger is this constraint. Okay, so what you observe typically is if you have landmarks which have been observed together and the mobile is moving around, so the closer they are together, typically the higher are these elements connected. This doesn't hold in general, but it's kind of not, it doesn't hold in all situations, but in most situations, it's something in observation you may do. Of course, it depends on your type of sensor, it depends how you model your problem, and how much uncertainty you add if you move. So if you have a high motion uncertainty, this correlation is typically smaller because the correlation come up because if you're moving from time step t, where you model the current pose of the robot and the position of all landmarks, and the robot moves on, you kind of add a node, x t plus 1, the current pose of the robot. What you mathematically do, you marginalize out the old one, and this gives you all these connections. And therefore, you get kind of the robot's pose and landmarks get they kind of they start to get dependent on each other, so they're not conditionally independent anymore. Exactly. What we have seen so far in our current problem, in our SLAM problem, is that most off-diagonal elements in this information matrix are close to 0, but they are not 0. They are small. And as I said before, what we are trying to do is to focus only, let's say, on the important ones and try to ignore the others or get rid of the others. And in this way, maintain a sparse matrix. So we have only a constant number of elements in this matrix, in the off-diagonal elements, that are non-zero. So as I said, I just said it here, set most links to 0 or in the void to fill in. It's not really setting them to 0, but it's kind of, for the moment, you can think about setting them to 0. But we will do it somewhat smarter than just setting them to 0. And if we have a sparse information matrix, this can actually dramatically simplify a lot of operations that we do, because we have only a small number of elements or a constant number of elements in my matrix for which I need to do an operation. And if I have a constant number of non-zero off-diagonal elements, I can do all my computations dramatically more efficient. And that's kind of the key trick of this sparse extended information filter is get rid of a large fraction of the direct links, focus on the most important ones, and avoid a fill-in, so avoid that the matrix gets dense. So kind of add only a small number of nodes and make sure the matrix doesn't fill up over time. It's kind of the key ingredients of the sparse extended information filter. And this is somewhat specific to the SLAM problem, at least the way which is presented here, because we have the assumption that we have an update step where the robot evolves and the number of dimensions which evolve which evolve in the motion update is small. The rest of the nodes are kind of static. So if the robot moves, it doesn't affect the landmarks. There are some assumptions in there, and this extreme efficiency of a constant time operation is only achieved in this context. Otherwise, I get a little bit more costly. But so it's kind of a little bit specific to the SLAM, although depending on the problem you have, you may come up with sparse variants of other problems as well. Okay, so it's kind of the very rough general overview clear at the moment, or should I elaborate something a bit more? We'll go through all the details, but if there's something which is unclear at the moment. Okay, perfect. Okay, let's look a little bit into the individual operations that we do. The first thing I would like to start with the measurement update step. What you see here on the left-hand side is the information matrix of our problem. What you see on the right-hand side is kind of the current scene that we have. So that's the robot, and these are 3 landmarks M1 to M3. And this is before any observation had been considered. So there's some initial uncertainty that we have about the robot's pose. This is shown here by this gray area. So we have some information about where the robot is. Let's say an initialization where we have a certain uncertainty we start with. And this is what the matrix looks like before any observation has been made. Is that clear? Okay. Now let's say the robot observes landmark M1 here. If the robot observes landmark M1, we will know something about M1, and we say there is a direct link between the robot's pose and M1. So if I given I know everything else and I fix I know XT, I can tell you something about M1. So if I kind of ignore for the moment M2 and M3, if I know the pose of the robot, given I have seen the landmark, I know something more about the landmark. So there's a direct link between them. And this leads to this kind of fill-in here of this matrix. So without moving, the robot takes a second observation. It observes now landmark M2. How would that matrix fill up? What do you think? Which blocks should be gray here if I see landmark M2?
The first 3 by 3 matrix to be
so this 3 by 3 matrix? That is not the case.
We can leave out the ones that correlates with M1.
the M1, M2.
Exactly. So these two elements will stay white. That's true. So we see the landmark M2, so which tells me something about if I have everything else fixed, the knowledge about the robot's pose will tell me something about this landmark M2. And now let's check to the other possibility that you indicated. What would happen if I would know? I just want to know if M1 and M2 are conditionally dependent of each other, given I know everything else. So given I know everything else means I know where the robot is. I have perfect knowledge about that. Not perfect, I know where it is. And in this case, so I would get kind of rid of this guy over here. I have only this block over here. If I know where the robot is, knowing something about M1 doesn't help me to estimate M2, because I know the robot's pose. So under the assumption that I know the robot's pose and M1 and M2 are conditionally independent of each other. That's different if I don't know the robot's pose. If I don't know the robot's pose and I know where M1 is, I can do a better estimate of M2. But under the assumption that I know the robot's pose, they're independent of each other. So there's no direct link between them here. Is this kind of clear why that is the case? Yes. Okay, perfect. Okay, that's how it looks like. So just to summarize that, if we integrate an observation, we add additional elements to this information matrix, and these are elements between the robot's pose and the landmark we observed. There we add something to the off-diagonal elements. And of course, we gain knowledge about this way gain knowledge about the landmark itself. Okay, so we have those elements which tell me which tells me something about the links I added. Okay, so we now did integrate our observation. Now it's time for a motion update. So the robot needs to move. What does it mean? The robot needs to move. The robot moves, let's say, from time step t, where the robot was at xt. It moves further on, let's say, ends up going to be over here, and this is new pose xt minus 1. So the pose is updated. And the previous pose is not taken into account anymore. Mathematically, it's marginalized out. If we can see that as creating a new node over here, and then getting rid of this node over here, that means that all neighbors of this node over here will become connected. So if I move over here, xt minus 1, I get rid of xt, these guys get connected. The reason for this is kind of by moving from xt to xt plus 1, I add additional uncertainty into the variable which represents the current robot's pose. But this uncertainty is kind of not added to the landmark I observed before. And therefore, those landmarks become correlated with each other because I eliminated this pose xt minus 1, so the old pose. This is so that I get new elements in here is something which results from the fact that I have a noisy motion and I only model the current pose of the robot and I ignore all previous poses. And therefore, I get this fill-in, what's it called, the fill-in of this matrix. So there are elements which get values in there. And this results from the marginalization step. So you marginalize out a variable, and this leads to a connection of all neighbors, or all elements which were connected with this node. Okay, so if you see that, so kind of you can see some of the information, at least some of the information, from these correlations are now moved here, so that we have an additional. So we have the wings get weaker between the current pose and the landmarks, because the robot moved on and got more uncertain about its new pose. So the links to the previous poses get weaker. They're a little bit smaller, but the links between the two landmarks get actually stronger, or is added because it wasn't there before in this example. Because in this moment, because the robot moved and added uncertainties to its state, knowing something about landmark M1 will tell me something about landmark M2. That's kind of the reason. And this happens in this form. So if you look to the motion update weakens the links between the robot's current pose and the landmarks, and it adds links between the landmarks. And therefore, this matrix gets filled up with new elements. And that's a problem for the sparse extended information filter, because we will lose sparsity. As we continue to map, this matrix will fill up, fill up, fill up, fill up. These values may be small, which are in here, but they are non-zero. This is exactly, if you do these steps as you've seen here, that's exactly which leads to the extended information filter. So your matrix will fill up, your information matrix will fill up with values. And therefore, the sparse extended information filter does a so-called sparsification step. This sparsification step is an approximation. That's the important thing to note here. There's not an exact operation. You lose something if you do that. And you lose accuracy. Your estimate of the Gaussian distribution will be worse if you do this step. But you gain computational efficiency, and that's the reason why people do that. Okay, so this is before sparsification. So, and we have the kind of this guy over here. This link over here corresponds to the value which is stored in here. We can say, okay, M1 is a landmark I've observed some time ago. The robot continues traveling. What we say now is, let's now ignore, after kind of the robot traveled a little bit, let's ignore this link. And simply get rid of this link. Simply throw it away. So this leads to the fact, if I throw that away, that we have 0 elements here in this off-diagonal, so there's no link between the robot pose and M1 anymore. So you got rid of this link. And you can see the effect of the sparsification means it took some of the information here and propagated here. So this link and this link gets stronger. Because again, if you make this assumption that given you, so the assumption is now, given I know M2, the new pose of the robot and the old landmark are conditionally independent. Again, this is an assumption. This is not an exact operation. I lose information here. I throw something away. But this approximation helps me to make my problem, to solve my problem in a much more efficient manner. That's kind of the overall goal in here. Okay, so what the sparsification does, it kind of means ignoring links, losing something by assuming a conditional independence. So it transforms the posterior in a certain way. So some of the information through the sparsification moves somewhere else. But it assumes a conditional, so the resulting belief has a conditional independence, and between the variables for which I kind of removed the direct link. So this is how the matrix will look like after the sparsification step. And if you know the number of elements which are currently in here, which are non-zero, is the number of elements I had after the update step. So the next motion update step generates a matrix with the same number of white and dark elements. Okay. And here is these are links between the robot's pose and features. So I kind of whiten out the direct links between the robot's pose and features. Okay, so that's kind of the key idea of the 3 main steps of the sparse extended information filter, which was the motion step, the measurement step, and the sparsification step, which is the additional step which which has to be considered in order to have a sparse matrix and maintain sparse matrix. And this leads us to the concept or so how do I realize this sparsification? And the sparse extended information filter does it by using so-called active and passive landmarks. And so it's this kind of a central element in this sparse extended information filter, how to realize this. And the active landmark is a subset of all the available landmarks. And it includes the currently observed landmarks. The landmarks I currently observe are in my active set. There may be some more, so let's say those which are observed in the previous timestamp, but the assumption is that this set of active landmarks is small and it's constant. It doesn't grow in size. So I just have, let's say I have 1 million landmarks in my environment and say just 10 are my active ones. And that means I only maintain direct links between the robot's pose and these 10 landmarks, assuming, let's say, I don't see more than 10 landmarks at the same time. Yeah. I mean, it is an approximation. In order to implement that efficiently, you need to typically set that to a constant size. You may be able to adapt that over time, but the gain by that is extremely small, and you can typically make an assumption. I don't see more than whatever n landmarks in the same observation. Again, it's an assumption. You anyway lose something, so it's not an exact operation. So you can make this another assumption that you'd say you won't, let's say, observe more than 10 landmarks or whatever your current setup is. And the passive landmarks are simply all other landmarks. And again, the key trick is a key approximation that I introduce is I only want to have direct links between the robot's pose and active landmarks, and I don't want to have links between the current robot pose and the passive landmarks. Okay, so if I go back to my example, which I had here, so this is an active landmark. This is a passive landmark. And this is a landmark which was active in the previous step and gets passive now, because I eliminated this link in the sparsification step. The kind of three things: active landmarks, passive landmarks, and those which have been active and now turn into passive landmarks. Yes, please.
When I have, like I say, I have in this example, I only observe one landmark at a time step. And if I say I observe two landmarks, would M1 be active, still be active? Yeah, so what you typically do is you'd say, let's say I have 10 landmarks I can maintain. So you would maintain the last 10 landmarks, and only the 11th landmark is observed, you throw out the landmark, the first landmark. Okay, yeah. So in this case, I just only drawn 3 landmarks. You could have more in here, and then the active set would be could be bigger. So it looks like, yeah, you can see that as a window in the sense of the active landmarks are those which I currently consider and ignore the direct links to all others. It's, yeah, pretty similar to that. Yeah. And what if I say I observe always 10 landmarks, but in a pose where I just see 5 landmarks? Okay, so maybe there's a misunderstanding. So the active set is not the set of landmarks I currently do see. Okay. All I see should be in there, but there can be more in there. Okay. So you'll keep typically, what the implementations typically do, they keep a constant number of active landmarks, n equals 10. It's my number, my personal number. Other people may use other numbers. And that's the number of active landmarks you maintained. If you observe 3, there are 3 that you currently see, and 7 which you haven't seen at the moment, but you still keep the direct links, because this is kind of the number of direct links you want to maintain. And obviously, the bigger this set is, the closer you are to the extended information filter. So if you make all landmarks active landmarks, you have your standard whatever EIF solution, or which give the same result than the EKF solution. But if you make your number, your set smaller, you will do a bigger approximation. So it's actually something you can trigger depending on how much computational resources you have available. You can say, okay, let's say I have a really fast computer now, so I can set n to 30. Or you have a really crappy machine, so n should be more 5 or something like this. So that's actually a parameter that you can set. The smaller the number of active landmarks, the faster, but the stronger the approximation that you do. So it will have a negative impact on your result. Any further question at that point? Okay, perfect. So we were talking about exactly active and passive landmarks. And the key idea is that of the sparsification is that the sparse extended information filter performs the sparsification at every step. So after every motion update and measurement update, it always creates this, carries out this sparsification step. As a result, I only have direct links, as I said before, between the robot's pose and the active landmarks, and I don't have links between the robot's pose and all other landmarks. And also, this strategy that I only have a small subset of active landmarks result in the fact that the landmarks have also a limited connection among each other. And the reason for that is when do I create links between landmarks? I create links between landmarks whenever the robot moves. I create a link between landmarks which are active at the same time. So if I limit my active set, I will also limit the number of links that I create among the landmarks in this active set. If there are only 10 landmarks in the active set, they can only, in this step, these two landmarks can be connected with each other. And there's, at this point, no connections with landmarks, let's say, which are further away. So I have direct links between landmarks which have been observed at the same time. Or had been not observed, which had been in the active set at the same point in time. Yeah, that's what's written here. Okay, so to summarize it, we have three main steps of the sparse extended information filter: motion update, measurement update, sparsification step. If I say that to you, I'm lying, because there's actually one. So far what you know, these are the three steps, but we are unfortunately in the fourth step. And any idea why we need a fourth step? It's very similar to the extended information filter. What was kind of one of the small disadvantages or structurally not so nice things about the extended information filter? Was it sufficient to maintain the information matrix and the information vector? Or was there something else I had to maintain? Well, there's a third quantity that I needed in the extended information filter, besides the information matrix and the information vector.
Kalman gain?
No, not the Kalman gain. So think about the nonlinear functions involved. One of the parameters of those nonlinear functions. So what's the input of the nonlinear functions in the Kalman filter, or extended Kalman filter? This function g and function h. G was the motion update, h was the observation function. What was the input? What parameters you need to put into those functions to get the result? The current state and maybe your control. Where's the current state? What's the current best estimate of the state? Where is it in my extended information filter?
The mean?
Yes, exactly. The mean is missing. Of course, I can reconstruct the mean, as was written here, by inverting the information matrix and multiplying it with the information vector. But the problem is this operation was potentially very costly. And therefore, what we said, we maintain the estimate of the mean additionally in order to put them into our nonlinear functions. And that's the same thing that we need to do here. So what we need to do, we have to put a new second step in here, which is an update of the state estimate of the mean. So we need to maintain the mean as well in an efficient way. And that's a problem. We need to do it in an efficient way. And we need that to compute the expected measurement. And also for the motion update, we need to know something about it. We need to know the mean. Otherwise, we can't predict where the system will end up with. And of course, we could compute it in theory in this way, but this is an inefficient way of obtaining that, and we would ruin our constant time approximation. There we need to add this additional step. Okay, so these are the four steps of the sparse extended information filter. I would like to talk today about the first step and the third step. So one is tricky. First one is a little bit ugly. And the measurement update is pretty easy. And it will probably take another hour or so to do that. Well, a little bit less than an hour, but approximately. And then the sparsification step and the update of the state estimate is something we're going to do next week. So it will not take full 90 minutes next week, but I tried to squeeze everything into 90 minutes last night, and it was simply impossible to do that without really eliminating essential steps that you need to know in order to understand the sparse extended information filter. So I said, okay, I'll keep it with kind of the only lecture here which is split up into 2 parts in this course, but I was unable to do it better, with having the feeling that you still learn what's going on. Okay, so let's look to the 4 steps of our sparse extended information filter. So if you do SciSlam, again, we have our 4 steps. As an input is the information vector at the from the previous point in time, the information matrix of the previous point in time, the mean estimate of the previous point in time, our current control, and our current observation. That's the input. And what the output will be, it is the new information vector, the new information matrix, and the new mean. Yep. Oh, okay. So that's kind of our goal. And so we maintain these 3 elements. It's not only information vector and information matrix. We additionally keep the mean because we need it for our nonlinear functions. Okay. So let's start with the step number 1, which is the motion update. Again, this is the kind of most involved operation. So don't shut off during these steps. We will derive a number of quantities that we need. Then we'll put those quantities together. So a couple of new variables will be introduced in the next 30 minutes or so. This is not that all these variables have a deep meaning. It's more the case that these elements we can compute and then we can put them all together and get an easy equation. So some of the definitions which will come up very soon may look a little bit odd, but you will see later, and hopefully later on you will see that you kind of compute 5 quantities and then you put them together and you get your result. That's kind of the easiest way to actually write that down. Any questions? Okay, perfect. Yes? The UT is the control command, so the odometry command or the motion command that I gave to the robot. So it's like go a meter forward. That's the motion update. The robot goes a meter forward. That's encoded in this UT. And that T was the observation that I obtained, like the observation of that landmark. So this landmark, which is a camera tripod at the moment, is 3 meters away from me, 90 degrees to the left. This is the information which is in that T. So the motion command which was executed by the robot and the observation that the robot obtained both at the current time step. So it's kind of the information I use to update, to go from my old belief to my new belief. From the belief at time t-1 to the belief at time t, I need to know which motion did the robot carry out approximatively and what it observed approximatively, or under noise. Okay, so before we start with the motion update, there's one thing that you may not know by heart. You should have seen that if you have taken linear algebra course, and this is the so-called matrix inversion lemma, which tells you how to, if you have a matrix of this form, where R and Q are quadratic matrices, and you want to invert this term, you can split this up into this long equation over here. This is something we will use. This is so-called matrix inversion lemma. And it can be extremely helpful, and that's why it's used often, if I know already something about this matrix I want to invert. So if I, for example, I know already R, the R inverse. So let's say I want to invert this matrix, and I know already the inverse of R. The only thing, if I look to all the individual steps which are written down here, so R to the inverted is already known. The only thing only matrix I still need to invert the matrix Q. So, and if I know R inverse already, I only need to compute Q inverse, and depending on the dimensionality of this matrix Q, that can be really advantageous. So if Q is a low-dimensional matrix, and these are functions which map it to a high-dimensional space, similar to these FT functions we used in the Kalman filter, and we know R to the power of -1 already, this can be computed very efficiently. And this is actually one of the reasons why we will use this in the sparse extended information filter. Because we don't know this matrix in our example that we see later on, but we can compute this efficiently. And if we can compute this efficiently, the only costly operation is inverting Q. And if Q is low dimensional, that's a very, very effective way for inverting such a matrix. Again, I'm not going to derive that. That's something you find in every linear algebra course, or in most linear algebra courses you should find that. There's something, just a lemma that we are going to exploit here in that course. Is it kind of, yes please?
But there's also an inversion of the things in the parentheses. So
yes, but that's true. We said Q is a low-dimensional matrix. And so if this is a low-dimensional matrix, so here P and Q, this is a transport, so it maps this high-dimensional matrix to a low-dimensional space, and you only invert in the lower-dimensional space. So this only makes sense if Q is a matrix with a low dimensionality. If Q has the same dimensionality than your matrix R, you typically don't win anything by this operation, unless you can exploit certain structures which exist. But the main gain is that Q is low dimensional, and you know already something about R inverse. Either you have approximatively computed it, you know it's sparse, and you then can compute the inverse fast, or you know the inverse from another computation, something like this. Then this is extremely helpful. Okay. It was just kind of having that said, looking into prediction step, how does a psi-slam prediction step look like? As I said, our goal is to compute the predicted information vector, the predicted information matrix, and the predicted mean out of my previous belief, or previous, oh, that should actually be t minus 1 here. I'm sorry, that should be t minus 1 in this line. And from the motion command from UT. So I want to compute the predicted belief. And as we know before, this update step is very costly in the extended information filter. So we want to do it better by exploiting sparsity. By saying, okay, my information matrix, this guy here is sparse because it's the output of the previous step of the sparse extended information filter. And my assumption is this matrix is sparse. And I want to show that if this matrix is sparse, I can actually compute these quantities here in a very efficient manner, given the assumptions of my active and passive landmarks, that I use active and passive landmarks. So I have active passive landmarks, and I know that the information matrix from the previous point in time is sparse. Then my goal is that I can compute all those elements very efficiently, especially I can do that constant time. Okay, so let's start from EKF. So we call it EKF slam, so it's just a copy-paste of the first part of the algorithm. Just as a reminder, we had this matrix F, which maps me, which has only one in the dimension that corresponds to the current pose of the robot, and then a large number of zeros corresponding to the number of landmarks times their dimensionality. And this was just used for mapping a small 3x3 matrix to this higher dimensional space I'm operating in. Okay, if I do that, I can express the prediction step in the EKF, so EKF, by taking the alt mean plus this mapping matrix and plus my nonlinear function. So this is kind of the element which tells me how do I update my the current pose of the robot with my nonlinear function. And then I can also compute the Jacobian, which was the identity matrix, plus again this mapping of whatever these small matrix over here to this higher dimensional space, add them to the identity. So I have the identity and only two off-diagonal elements, which are these two guys, are non-zero. This was the results from the first derivative. So it's Jacobian, which I compute. These are the partial derivatives of my nonlinear function. Okay, so this is all EKF, and then the first step in the EKF was I have my Jacobians times my the previous estimate of my covariance matrix plus the noise term. Again, here the noise term by a 3x3 matrix mapped to the higher dimensional space, so that this is the noise term, which is everywhere 0 for all landmarks, and just only for the robot's pose it's non-zero. That's what I have, and I want to start from this operation to derive the sparse extended information filter step. The first thing I do is do a copy and paste of these three elements, or basically a copy and paste of the ideas, And then I start with this term over here and say, okay, the first thing I want to compute is my information matrix. The information matrix is the inverse of the covariance matrix down here. So in order to compute omega bar t, I take this expression here and invert it, and then see where this takes me. Okay. From the notation point of view, I again have so now I have my Ceph algorithm. I have again my fx, it's exactly the same function I had before. So this was my copy-paste operation of this guy. And I have my my vector delta, which is exactly this vector over here. So if I take the new mean is the old mean plus ft times my delta. And the large delta is exactly this expression over here. Oh, these are my three terms over here. And now I want to use this to compute the predicted information matrix at time t by inverting this expression over here. And that's exactly what I do. I say, okay, my information matrix is the inverse of my covariance matrix, just by definition. And just by definition, I expand it in this way, and I invert it. Right? So this is just copy-paste. Then I say, okay, let's define a new quantity, phi, over here, which corresponds to these three elements. These three elements give me phi. If I define a vector matrix phi, or phi to the power of -1, sorry, for these guys, that's how my information matrix is computed. Okay? So if I can compute this expression, the overall expression, including this inverse, efficiently, I can obtain my information matrix efficiently, right? Okay. So if I defined phi to the power of -1 to be these terms, then phi is these terms inverted, and I can express it in this way. So that's just, if I define the information matrix in this way, this is the definition of phi. Okay, so let's see if we can compute this term over here in an efficient manner. So we have phi to the power of phi inverse plus RT, this is a noise term, inverted. It's just exactly what was written on the previous slide. I can say, okay, this matrix RT was the noise term of the motion update, which is a low-dimensional matrix, 3 by 3, mapped to a high-dimensional space. That's it. So I can write it in exactly this way. Okay. Which pattern do you see here? You see something we discussed before that we could exploit now. So we want to compute an inverse of one matrix. This can be expressed by a matrix plus f, r, this is low dimensional, and f.
It's the lemma.
Exactly. So this is exactly the pattern I've seen for which I can use in the matrix inversion lemma. So the next step is now just apply the matrix inversion lemma, and you get exactly this term. It starts to get a little bit ugly, but we don't care really about the individual terms. The important thing is here that this guy in here is a 3 by 3 matrix. Because this is a 3 by 3 matrix, and this maps just takes out the elements of a small part of this matrix phi, maps it to a lower dimensional space, and inverts this matrix in the end. So it's inverse of a 3 by 3 matrix. That doesn't hurt. It's constant in the number of features or landmarks I have at all. So that's perfect for me. The next thing I do is I know that these two elements, they are all zeros except the 3 by 3 block, which is the identity matrix. Okay, so that's all good. So we'll take a dense 3 by 3 matrix, maps it to a higher dimensional matrix, which is everywhere 0 except this 3 by 3 block, which may be populated with values. Right? Is that clear? So this expression over here is a large matrix which is 0 everywhere except in the upper 3 by 3 block. Because this matrix over here, which is a 3 by 3 matrix, which may be densely populated, I don't know, this is mapped to the high dimensional space with a dense 3 by 3 block, and the rest is all zeros. Okay. That's good. And the only thing I need to do is I multiply this expression with my matrix phi. So if and only if this matrix phi is a sparse matrix, that means it is basically has diagonal values and is everywhere 0 except of a constant number of non-zero elements, then I can actually do all this computation in a constant time operation. Because this operation, just the 3 by 3 block, the rest is all 0, will only be multiplied with a constant number of elements in this matrix phi. So basically everything is 0 except a constant number of elements, and I multiply it with a small number, with a small matrix, only have a constant number of operations I need to carry out, independently how large this matrix phi actually is, if there's only a constant number of non-zero elements. And I have means for fastly retrieving those non-zero elements, but that's something I assume. Okay, so that's good. So what I now do, I take this whole expression, everything here, and define this as a new matrix called kappa T. So kappa T I can compute efficiently if and only if this matrix phi is sparse. So I need a kappa and I need phi, and if I have both of them, I can actually compute my information matrix. Okay, so the next question is, how do we actually compute this guy efficiently? Something we said, if it is sparse and if, how can we compute that? Because if we look to the definition, how we defined it here, so this quantity over here was the inverse of phi. And now I need phi not inverted. So the question is, how do I obtain phi not inverted? Okay, so let's look how this function looks like. So next goal is, okay, actually this. The next goal is, we want to do that, compute this element here as a constant time operation, because we still want to achieve constant time operation, if this matrix is sparse. So under the assumption that the information matrix we get in from our previous operation is sparse, that's the assumption we do, then we want to say, then we can actually compute this guy over here in constant time. That's what I want to do. Okay. Sorry, I mixed up the order of the slides. So what is the inverse of my Jacobian? So what is here is just the definition of my Jacobian. So it was the identity matrix. And then I mapped this small block over here, which just had, whatever, 2 non-zero elements, to this higher dimensional space and add that up. Okay? And then I have, the problem is I have to invert this matrix. How do I get that inverse? So if I look to this matrix, this can be written as delta plus a 3 by 3 identity matrix plus 2n by 2n identity matrix down here. And these two elements are zeros. Is that clear why this can be written in that way? Yes, please.
Is n now the number of possible landmarks or the number of...
No, the overall number of landmarks.
Yeah.
So the overall number I maintain in my filter. Okay, so and I want to compute the inverse of this guy. To compute the inverse of this guy, I can exploit the fact that this is a kind of a matrix I have here. This is a matrix, and this is a matrix, and this is a matrix. And these two matrices are zeros. So it's like you can see there's a matrix which consists of 4 submatrices where the off-diagonal matrices are zero, only zeros. And if this is the case, I can, to compute the inverse of the overall matrix, I can compute the inverse of the individual blocks which are non-zero. So it's the inverse of this guy and the inverse of this guy. So this power of minus 1 moves in here. The inverse of the identity is the identity, so there's nothing to do down here. And here it's the inverse of delta plus the identity. This is a really great thing. Why is this a really great thing?
Because it's a small matrix. So
Exactly. So this matrix here was a high dimensional matrix, 3 plus 2n, and I had to invert it. And I simplified the problem in this way, exploiting the special structure that this Jacobian has, so that I only need to invert a 3 by 3 matrix. That's a big win. Because that's something which is constant in the number of landmarks. I don't care how many n's I have here, because this doesn't change. The only thing I need to do is actually update this guy here on top. Okay, so exactly 3 by 3 matrix at the big thing. Okay, so what I can then do is I can say, okay, I kind of change this matrix. I just pull out the identity, so it's a 3 plus 2n by 3 plus 2n matrix, plus the rest, and so I had the identity which I have to subtract from this term, so it's minus the I3 identity. So it's just pulling out an identity matrix. And if I do that, I can actually write this, okay, I kind of find a new matrix, which is this matrix, and say, so the Jacobian is just an identity matrix, a large identity matrix, plus this additional term over here, which I can write in, again, my mapping from the low dimensional space to the high dimensional space, plus this expression over here. Are you still everyone on board? Okay, so our goal is to efficiently compute overall. We are currently in the computing the information matrix. We said, okay, we can define the information matrix at the inverse of the covariance matrix. This consists of two terms. The first term is something we defined as phi minus 1. The second one was our noise term, R. We use the matrix inversion lemma, arrange these things in a nice way. Say, okay, now we have all cool matrices. We can solve that quickly if my matrix phi is sparse. And now we are looking in how can I actually obtain phi and why is it sparse. And the first step to compute phi is something we did already. It's computing this term over here. This is this guy. Oh, no. This guy, but it's just transposable. And we know that this guy is already sparse. This is something we know. So we can put that together, and we have this expression over here. So we can obtain this expression over here. And this was just the matrix that we defined before. So this psi is exactly this term over here, where this is a 3 by 3 matrix, so everything is super efficient. And we just need to multiply. So we have these two matrices. We just need to multiply it with a sparse matrix. So we have a matrix which is just identity in a little bit times a sparse matrix times the identity in a little bit. So we always have the identity, just copies everything over. And then we have this a little bit multiplied with a constant number multiplied with a little bit. And this little bit is also constant with 3 by 3 times constant number, which I don't know exactly how large it is, but it is constant, times the 3 by 3 blocks. So that's something which is independent of the size of the overall matrix. And that's kind of the key thing. That I can compute this term by having kind of 3 sparse matrices. This guy is sparse, this guy is sparse, this guy is sparse. And it's actually better than sparse because they are basically, those Jacobians are basically identity matrices. For identity, I don't need to do anything. Just have a small number of elements which are non-identity, and they introduce some cost, but it's constant. It doesn't depend on how big that matrix is. Okay, so just to kind of repeat what I said. So these matrices G are identity matrix except of 3 by 3 blocks. The information matrix is sparse, and this implies that this term can be actually computed in constant time. Of course, sparse, identity with a little bit, identity with a little bit. So I can, if I do kind of an in-place update, so I just update this estimate without needing to copy it over in memory, and the copy operation would be linear on the side of the matrix. But if I do that in place in that matrix, that can be done efficiently. So it's clear what I mean with in-place operation. So you have a large memory block which you have allocated, which may be huge, and if you copy that over, the copy operation would be extremely costly. So what you do is you do the operation in place, so in memory, you just override the individual values in your matrix you need to change. And although the matrix is large, you need to change a small number of values and you have the result. That's what's in place. So you can't really, if you have to copy this, you would have to copy this matrix. They're going to be expensive, but you can kind of change it in place. Okay, so we said, okay, this is again a more sophisticated explanation why this is a constant time operation. So we said, this was our matrix before. We said this is identity plot 3 by 3 block, identity plot 3 by 3 block. This is sparse. So I can multiply that out, and I obtain this expression over here. And so I have the old information matrix over here. And then again, there's again identity 3 by 3 blocks times the sparse matrix plus the sparse matrix multiplied with an identity matrix in 3 by 3 blocks. So this is all easygoing. And here again, the identity 3 by 3 block, except 3 by 3 block information matrix and this guy. And these are all operations which can be done efficiently. This can be seen as an additional lambda, which has a constant number of non-zero elements. And this just needs to be added to the information matrix. Yes, please.
When I have all these zeros,
Yep.
how do I tell my computer that it doesn't have to calculate anything?
So what you typically do is there are means for representing sparse matrices, and they basically only store elements which are non-zero. And there are efficient ways for indexing that. So you can do it, for example, one way to do this is using hash table. So you have a hash table, and the key to your hash table is the row and column index. And you compute from this ij, you compute a hash value, you look up in your hash table, and you retrieve the element. So the hash operation is constant time, so you can in constant time obtain that, given that you have the index. And you can even iterate over those values depending on the underlying hash table model that you use. So that's one way to implement a sparse matrix. Okay, just to sum that up, we compute this guy over here, which was the identity matrix plot a little bit. Then we can use this to compute my lambda. Based on the lambda, I can compute my phi. Then I can use my phi to compute my kappa, and my kappa to compute my information matrix. Again, I introduced a few expressions over here, a few variables over here, but these variables, if you don't introduce those variables, I can't put that stuff on the slide, it gets very, very huge. And these are individual values which can be computed in the individual operation, put together, and I obtain my information matrix. So I can turn that exactly into an algorithm. So these 3 steps we have seen in the beginning, and then I compute all those individual values and put them all together. What we have done up to line 9 of our algorithm, we computed the information matrix for the prediction step. But the information matrix is only part of the game. We needed also the mean and the information vector. But it was the hardest part, so we can, from now on, it's not that tricky anymore. The next thing was we need to compute the mean, right? But the mean is easy. It's kind of what we know from the EKF world. We have the predicted mean is just the old mean, which I luckily maintain. That's not an advantage for me. And this is this matrix, which maps from the low-dimensional space to the high-dimensional space. And it just maps my vector delta. And the vector delta was kind of the elements of the nonlinear function. Kind of the nonlinear function was kind of the old value plus some delta. This is exactly this delta, as we defined it before. So it's just kind of what results from the odometry motion model. Exactly here the values, just copy paste from the algorithm. So this was the matrix, and this was kind of the so the nonlinear function g. Was my x prime was g of x, and this was written in a way that there's x plus some delta. And this was kind of the structure. And if we have this structure of g, this is exactly the delta you've seen there. That's it, we're done. That was easy, right? So we have new mean, this old mean, plus our delta, which we can easily compute. So we now have computed the information matrix. We have computed the mean. The last missing part is the information vector. Okay, what is the definition of the information vector? Written over there. The information vector is the inverse of the covariance matrix times the mean. So that means my not good in drawing these guys. Can also write this as the information matrix times the mean. Ah, that's cool. That's all, basically everything we know. Oh, sorry. We know all that. So it is the information matrix times the new mean, which can be expanded like this. The problem is if I would compute these guys in this way, that will be a linear time operation, right? Because I have a vector, the mean vector, which is 3 plus 2 n-dimensional. And I multiply that with an information matrix, which is sparse, but at least I need, it's a linear complexity that this has. That would be stupid. I mean, we did all the magic tricks to get it a constant time, and then the information vector screws it up. So it's not going to happen, but therefore we are not done in that step doing just a simple operation, but we have to change our expressions a little bit. But what's written over here is basically exactly what we had here on the blackboard. And now we can say, okay, let's expand this over here. So the old mean is the old information matrix inverted times the information vector. So click over here. So this is this equation over here. Plus nothing changed over there. Okay, now I can kind of trying to get rid of the brackets. Then I have the new information matrix times the inverse of the old information matrix times the information vector, and here the predicted information matrix times my mapping function and my delta t. Now what I can do now is I just look to the first term over here and just add two or take the first element over here, the predicted information matrix, and just add and subtract an identity matrix to it. So you can say, okay, that's an identity matrix, another identity matrix. Exactly. I just add them up so that I take plus 1 minus 1. So nothing bad happens in here. Then, or actually, wait, these are not ones, these are zeros. That's completely stupid what I wrote here. It's not a multiplication, it's a sum. These guys are zeros, these are not ones. Yeah. So I add twice 0 by adding the matrix, subtracting the matrix, adding the same matrix, subtracting the same matrix. Right? 0, not 1. That sucks. That's the 0. Okay. And now I can just rearrange those, reshuffle them a little bit. So then I write that as this minus this guy minus this guy, and multiplied with all the rest, plus this guy multiplied with the remaining, this remaining part. So I group these two guys together, this one together, and then I partially multiply out this element from the matrix. So I obtain this and this, exactly the same, times these guys over here, plus this element times these guys over here, which is sitting over here, and the rest maintained there. And now, nice that I defined some of those values before this kappa and all the ugly terms, because I can reuse them here. That's the reason why I did that. So this guy is simply minus kappa. Perfect, I already computed it. This is equals to lambda. Perfectly, already computed it. This guy here is my old mean. Perfect, everything done. This is an identity matrix. That simply is easy. This is information vector, great. And the remaining terms I had. So I can write that as, just rearranging the elements a little bit, moving that to the front. So the new information vector is my old information vector plus some extra elements in here. Now remember, we had those matrices, and we had nice properties of those matrices. For example, my lambda matrix had this function. It's basically everywhere 0. There are just a few elements which are relevant. And then I subtract something else, which is basically 0, just a few elements. And I multiply that with a matrix, with a vector, which is fully filled. But these guys, these matrices, basically 0 everywhere except of a few values. So I can kind of cherry pick the dimensions from my previous mean to perform the update. So the resulting vector here is basically 0 everywhere except of a few elements. And again, therefore, I can do that fast. Constant number of blocks, elements I have to look up in the mean, previous mean, and it's something I can do in a constant time operation. And then I have just this matrix here again, which is basically everywhere 0 except of a 3 by 3 block. Multiplied with a sparse matrix, that's great. Everything 0 except of a small blocks multiplied with a sparse matrix perfectly can be done in constant time. Yeah, so that's it. Exactly, that was my equation. Nothing else which needs to be done here. So I can turn that into the algorithm. So this is my information vector that I computed exactly as I written it before. This is my my mean exactly as it was done, and we are done. Perfect. So we have the predicted information vector, we have the predicted information matrix, and we have the predicted mean. Yeah, we're done with the first step of the algorithm, which was the prediction step. But that was the hardest part. The rest is really not that tricky. So what we've seen here is, under the assumption that my input information matrix from the previous point in time is sparse. We assume this guy must be sparse. That means it has only a constant number of non-zero off-diagonal elements. If this is the case, and I can exploit that the motion update only affects a small constant subset of the dimensions of the state vector. It's just the motion of the robot only affects the pose of the robot. It doesn't affect the landmarks. Under these two assumptions, I can actually end up computing those three quantities in constant time, not doing any further approximation than what we have done before. Just by exploiting that this matrix is sparse. If this matrix wouldn't be sparse, the incoming matrix, everything would screw up. And that's the reason why if you do the regular Kalman filter or the regular information filter, and you don't exploit any sparsity and you don't exploit that only a small subset of the dimensions are updated, then it's simply a costly operation. Okay, so I want to say the next thing I would like to discuss is the measurement update step, because it's kind of the two importance, the kind of key element that we know from the extended information filter. Therefore, I decided to present both the first and the third step first, ignoring the stuff in the middle. Then the second step and fourth step, that's something we're going to do next week. Okay, let's look to the measurement update. This is identical to EKF-SLAM. So the first part is just copy-paste from EKF-SLAM. What do? I have a matrix Q, which tells me the uncertainty of my observation. I assume here again I have range and bearing observations, as we did that for the Kalman filter EKF-SLAM. I have my observation, which consists of this range and this bearing observation. I assume to have known data association. So it was the assumption that whenever I see a landmark through my sensor, I know that this is a landmark, whatever J in my state representation. So I know what I'm observing. Then I have this initialization. If I've never seen the landmarks, I need to initialize it. And otherwise, I compute the predicted observation and the exactly these delta terms that we used for the Jacobian. And again, here I need the mean estimate. Therefore, it's important to have the mean. So I need the mean for the prediction step, and I need to compute the mean for the correction step. in order to compute the predicted observation. And then I have, again, this matrix H, which is the Jacobian of the observation function, exactly the same as we did in the EKF. The only difference compared to the EKF are these two steps over here. This is because we are now computing the information vector and the information matrix, and not the mean and the new covariance matrix. But these are exactly the equations we put in from the SIFE, because this was kind of the update step in the SIFE. So everything, kind of how to initialize landmarks, how to compute the Jacobian, it's all exactly as it was in the EKF. The only thing we don't need to do, we don't need to compute this Kalman gain and weigh them. This is done as it was, as we derived it for the EIF. These terms over here. Yeah.
Yeah, the HIT matrix.
Yes.
This is just for one landmark, right?
This is for one landmark. Therefore, we have this loop over here.
Yes.
And yes,
that
each landmark that I observe.
Yes.
Yes. You can do two things. You can either update them separately or you can stack them in a matrix.
Yeah.
There's a subtle difference between those two things. The subtle difference is you need to do an inversion of this. There's somewhere an inversion involved of this matrix Q. The more elements you stack, the more costly this operation is, unless they all have diagonal elements. So if you have if you observe two landmarks at the same point in time, when given you know the pose of the robot, those are independent of each other. You can do that one at a time, with a for loop. Or you can stack them and do that. Yes, you can do that, because the update is at the same point in time. So it's really, as it is written there, the algorithm works perfectly. So it means if you observe the landmarks, you don't have, between those two landmarks you observe at the same time, you don't have any links in the off-diagonal elements. If you have that because you have a sensor which provides you with that information, then this may change the game. But as long as this is not the case, so if you would put in a second observation here, that would be a diagonal matrix where you have, again, the same values repeated over here, there's nothing wrong with that. Okay. And yeah, that's it. Measurement update done. Well, that was easy. It was just copy paste from the Kalman filter that we did before, and then replace these two lines from what we have derived last week from the EIF. So it's just taking two parts we did already, stack them together, done. So that means we are done with the motion update and the measurement update, and both are constant time operations. So I only needed to change a constant number of elements in my information vector and a constant number of elements in my information matrix and a constant number of elements in my mean estimate. And that was kind of the cool thing. It's a constant time operation under the assumption that the incoming information matrix is sparse. That's it for today. What we're going to do next week, we say, okay, we have that now. We know how we're able to do that. How can we actually ensure that this matrix is sparse and stays sparse over time? So what we'll do next time is we do the sparsification step. That's where we're going to start next week. And then we will also discuss the update step. So yeah, what the update step does is how do I obtain the corrected mean given the predicted mean in an efficient way? Because I need that to compute the predicted measurement. To compute the predicted measurement, I need to know where the robot is according to the belief, and therefore I actually need that information. Okay, that's it from my side for today. You're released a little bit earlier, 5 minutes earlier than that's typically the case. What you should do at home is kind of revisit the concepts here. Make sure you understand what's going on. Make sure you understood the key concept. And then we're starting next week with the sparsification and the update step. It doesn't hurt looking to the slides of next week and let's say read one through the sparsification, which is also maybe non-trivial to prepare for next week. And then we will probably need whatever 1 hour next week to finalize the sparsification and the update step. for the sparse extended information filter. Then we will do a short wrap up about what we have done so far. So we will revisit the quickly the Kalman filter, extended Kalman filter, UKF, EIF, SIFE, just very, very briefly in 10 minutes to kind of wrap up everything we have learned about the Kalman filter so far, about Kalman filtering and Kalman filter families for addressing the SLAM problem. And then in 2 weeks, move over to the next paradigm and look into what's next, what's behind Kalman filters. That's it from my side. Thank you very much and see you next week.